This is a film about bubbles. To most people, bubbles are just toys children play with. But they're so much more. They're amazingly powerful tools that are pushing back the boundaries of science. I'm a bubble physicist, and the reason that I care about bubbles is that they're part of how the planet works. Out at sea, breaking waves generate huge plumes of bubbles, and those bubbles help the oceans breathe. Then there's the soap bubble with its delicate, fragile skin. Something we can all see and touch, yet it can tell us about how nature works on scales as large as our solar system and as small as a single wavelength of light.
Here, we've identified what we think are interesting questions that will open up new areas in mathematics.
We're learning that bubbles influence our world in all sorts of unexpected ways. From animal behavior to the sounds of running water, and even the way drinks taste.
The bubble cavity collapses. It can eject a tiny champagne jet up to several centimeters above the surface.
And perhaps most exciting of all, we're only just beginning to appreciate the potential of bubble science. But there's still so much we don't know about bubbles, so much to learn. These little things are full of secrets and surprises. Welcome to my world, the wonderful world of bubbles. Bubbles really matter to our planet. 3/4 of the Earth is covered in water, and just under the ocean's surface are billions of bubbles, formed as breaking waves drag air underwater. Right in front of our eyes, these bubbles are playing an important but invisible role. At a bubble, the ocean and atmosphere meet, and both are affected. And this is all thanks to just a handful of a bubble's fundamental properties, which we're learning about in ever more detail. And that's the focus of my work, both out at sea and here in my laboratory at Southampton University. If we understand the basic processes of bubble formation in different situations in the ocean, we'll be able to use that information to improve weather and climate models. And you wouldn't think that something so small could affect something as big as a weather system, but it can. Let me start with a simple question. What is a bubble? There are two different but related kinds. The first are these, underwater bubbles, the focus of my research. But the bubbles most people know are these, soap bubbles. Despite being made of the most mundane of substances, soap, air, and water, they're incredibly beautiful. These ethereal objects and the lessons they can teach us have fascinated scientists for decades. As the most famous of Victorian physicists, Lord Kelvin, said, "Blow a soap bubble and observe it. You may study it all your life and draw one lesson after another in physics from it." Kelvin was fascinated by the way the delicate skin of a bubble affected the behavior of light. and in particular the beautiful colours it reveals. Just look at the fantastic patterns on this soap film here. They're there because the film is so thin. It's only a few hundredths of the diameter of a human hair. That means a soap film is around the same thickness as a single wavelength of visible light. The different colours on the film correspond to different wavelengths of light in the spectrum. And what fascinated Kelvin and scientists like him was, how is this possible? How can something so thin possibly exist? And the answer is to do with the weird nature of something very everyday: water.
So this is just fresh water. And one of the things we associate most with liquids is droplet formation. So I'm going to use my sleeve and put some drops of water on it. And they're really pretty. So you can see that these droplets are sort of curved inwards. And the reason for that is that the water molecules on the surface are being pulled into the bulk of the water really strongly just on one side. So water behaves as though it's covered with an elastic skin. And we call that surface tension.
Surface tension is one of the most delicate and intriguing forces in all of nature, and its causes lie with the shape of the water molecule. Something very strange happens when hydrogen and oxygen, the atoms it's made of, join together.
And the reason for that is that when the hydrogens join the oxygen, the molecule doesn't become a straight line, there's a kink in it. And so overall, one side of the molecule has a slight positive charge and the other side has a slight negative charge. And what that means is that when other water molecules come close, the positive side of one is attracted to the negative sides of the other. And so overall, the bonds that attract water molecules to each other are really, really strong.
These bonds mean that the molecules in the body of the water are pulled equally in every direction. But the molecules on the surface are pulled inwards, making the surface of water like an elastic sheet. This is critical for understanding all the amazing properties of soap bubbles. But how? And crucially, why can't you make bubbles with pure water? Why do you need soap? This was a surprisingly difficult question to answer. And the key to solving it came not from the great men of Victorian science, but from an obscure house in Germany. Some of the earliest experiments on surface tension were done by a German lady called Agnes Pockels, and her work was only published in 1891. I've got a copy of the paper here. And the paper is prefaced by a note by Lord Rayleigh, who was a very famous English physicist. And this is what he said, and this was his note to Nature. I shall be obliged if you can find space for the accompanying translation of an interesting letter which I have received from a German lady, who, with very homely appliances, has arrived at valuable results respecting the behaviour of contaminated water surfaces. And the reason that he wrote the preface is because Agnes was born in 1862 in a time when women were not allowed to study physics to any great degree or to go to university, and so she was not allowed to publish the paper herself. The first thing Agnes did, just using the equipment in her kitchen, was come up with a new and incredibly clever way of measuring the surface tension of water. I've got a version of her experiments here, and what she was looking at was how hard surface tension can pull. And she had this experiment. Now, she describes it as a small disc at the bottom, and that's been interpreted as being a button, so I've got a button on mine. And my button is held by elastic thread, and so the elastic thread is pulling upwards on the button, and if I let it go, you'll see it hangs quite a long way above the water surface. But when the button is touching the water, the surface tension is pulling the button down and the elastic is pulling the button up. And Agnes realised that you could measure surface tension by adjusting the pull from above just until you got to the point where the button was just about to break away. And that moment there is when the forces are balanced. So she had scales, effectively, that measured how much upward pull there was. And so she knew how much downward pull the water was providing. But what Agnes did next was the really clever bit. And it would be the key to understanding soap bubbles, why they exist and what they do. Agnes realised that you could also use this device to measure how surface tension changed in different situations. So what she did was she contaminated the surface. This is just detergent. So I'm just going to put a few spots of it nearby, and as I put them on the water surface, the detergent is lowering the surface tension, and so the button will pop off the surface. Agnes's measurements showed that adding soap to water reduces its surface tension. That's a crucial observation. It's the answer to the first question about soap bubbles, and why you can't make bubbles with clean or pure water. If you make bubbles in clean water and they rise to the surface, they make a spherical lid like this for a very short period of time, and then the surface tension of the water is so strong that it pulls this film and breaks it up into lots and lots of tiny, tiny droplets. So clean water has surface tension which is far too strong to let foam like this last, and that's where the bubble bath comes in. The soap molecules in the bubble bath position themselves at the surface of the water, changing how the surface behaves. So if we look at one of these bubbles here, the reason that this thin film can exist for so long is that the soap molecules have reduced the water's surface tension. So the pull to make that pop isn't as strong as it was. So the soap molecules are allowing these thin films, beautiful thin films, to last for a really long time. But the fact that soap and water can combine to make something so thin doesn't just mean that we have beautiful toys to play with. Soap films are helping us solve the toughest mathematical problems in nature. These are the storms in Jupiter's atmosphere. This is a massive example of one of these tough problems, the complex ways that fluids flow. And this is that process, recreated on the surface of a soap bubble. Fluid flow is really beautiful, but it's also really difficult to study. And soap films can help, because by following the colours on the surface of the film, you can track how the fluid is moving. And that gives you a way into studying systems that are otherwise either inaccessible or invisible. These are clouds above the Indian Ocean. They form these patterns, vortices, as they get blown around an island. These and other flow patterns, for instance the way that water travels around a solid object, can be replicated and studied in soap films in a laboratory. And it's not just questions about fluid flow that soap films could help answer. Soap films are mathematical problem solvers. You can see it in their almost uncanny search for geometrical perfection. Left to themselves, they're perfect spheres. But they can do other tricks too. For instance, what's the most efficient way to join these 4 points? Blow on the soap film and it finds precisely the right answer. all these angles are exactly 120 degrees. Soap films do this because of surface tension, pulling in every direction on the bubble's surface. That means a soap film will always try and minimize its surface area. Free-floating bubbles are spherical because that's the shape with the least amount of surface for any given volume. The soap film connects the 4 points like this because it's the arrangement with the least surface area. And what's really amazing is that this ability of soap films to minimize their area is still at the forefront of science. In nature, these are common occurrences. They're called singularities, sudden changes in shape or structure. They're incredibly hard to describe and understand mathematically. And that's where soap films come in. Here's one, captured by a camera that slows down time 50-fold. Stretched between two hoops, it suddenly splits into two, instantly changing from one shape into another. This is Professor Ray Goldstein at Cambridge University. For him, the soap film could be a vital clue to understanding the singularity.
You see them all the time. When a drop of fluid breaks up, when certain structures come off of the sun, they form these beautiful arcing filaments and give rise to huge ejections from the sun. So on every length scale you can imagine, and for many decades, physicists and mathematicians have been interested in understanding the mathematics of what we call the singularity, when the moment that rearrangement happens. And they're so nonlinear, they're so hard to solve, that we really are at the infancy of the study of these kinds of singularities. What we hope is that we'll see a pattern emerging that will teach us something deep about these kinds of transitions.
And the surface tension on the soap film is the key. It ensures that they perform their shape changes with the minimum use of energy, which is the preferred way nature operates. They're also relatively easy to study in the lab.
For us, this is a laboratory example of a singularity that is similar in its structure to many kinds of singularities that occur in nature. It has the advantage that we can study it in great detail in the lab. We can do these high-speed movies, we can do some mathematics, we can vary particular quantities like the viscosity of the fluid or the surface tension, the size of the wire, whereas it's difficult studying the sun since we can't get near the sun to fiddle with it. So by looking at these soap films in the lab, where we can control everything, we have the hope of testing our theories in a way that allows us to go back and forth and refine them to the point that we can finally say, yes, I think we understand what's going on.
It's incredible that we can study the sun with the help of a soap film. That it might unlock the secrets behind some of the strangest phenomena in the universe. But amazing though they are, I want to show that soap films and soap bubbles are just the start of the story. I want to return to the other kind of bubble I mentioned, the kind I study, underwater bubbles. These are pockets of gas that are trapped within liquids. They're a treasure chest of scientific riches, and they affect everything from animal behavior to the taste of champagne. And they make a surprisingly important contribution to the Earth's climate. I want to start the story here in this pool, which is equipped to make huge plumes of underwater bubbles. We'll see these underwater bubbles dramatically change the properties of the liquid they move in. And that can be incredibly useful. In this pool, it's used to help train springboard divers. Diving pools like this have a big air reservoir underneath. They can send a big plume of bubbles up, and that means that when a diver is learning a dive, if they come down and instead of hitting flat water, they hit bubbly water with a lower density. So that instead of having a short, sharp shock, they get slowed down but over a longer period of time. So bubbles help divers train. And it's because the bubbles do this that, although I haven't done any diving for a long time, I'm prepared to try it again. The reason bubbles make water less painful to dive into goes to the heart of what a bubble actually is. A bubble is what you get when a liquid like water and a gas like air that really don't want to mix are forced together. The surface tension of water tries to squeeze the bubble into having a smaller surface area. And the air is rising as fast as possible. But during their brief coexistence, they form something new. A mixture much more substantial than air, but considerably softer and less dense than water.
So happy to get around. That happened really quickly. But it's good. I did it. Haven't done that dive for 6 years. Bubbles are good, right?
Animals that spend a lot of time underwater have evolved some incredibly ingenious ways of exploiting the fact that bubbles reduce the density of water. These are emperor penguins, diving to depths of 10 meters. They store air in their feathers, which they release as clouds of bubbles as they zoom upwards. This makes the water around the penguin less dense and much easier to move through. It means the penguins can travel up to 50% faster than if there were no bubbles. I love this because it shows just how useful bubbles are. It helps divers like me get into the water safely, and it helps the penguins get out safely. And in the shipping industry, there's intensive research going on into how bubbles can make water less dense and easier to move through. This tall steel drum spinning inside a cylinder of water is part of an experiment at a Dutch university. Engineers here stream bubbles in varying amounts and sizes across the drum's surface to learn how they reduce friction from the water. And in late 2012, Japanese shipbuilders Mitsubishi fitted a bubble lubrication system under one of their ships. They hope that this will reduce fuel consumption by up to 15%, potentially saving billions of pounds. Bubbles are proving to be incredibly useful to the modern world. The next really important use of bubbles is connected to one of their most surprising properties: their relationship with sound. This has all sorts of consequences, everywhere from industry to medical research. But for me, it's a fabulous tool because sound lets me monitor what bubbles are doing in the ocean. And this will help me understand their role in our climate.
It goes pop, 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 pop.
Bubble acoustics is a branch of science in its own right, but it begins with the simplest of observations.
So I have a tank of water here with a nozzle down at the bottom, and I'm going to feed air into it by pushing on a syringe here. So I can see there's air coming along the nozzle. And I'm just going to make one bubble at a time. And here's the thing, if you put your ear up against the tank, you can hear it's going ping, ping, ping for each little bubble. Every new bubble that's formed like this is like a little bell being hit with a hammer, and it goes ping. If you pour out a drink or that you hear a babbling stream, this is the sound you're hearing. You're hearing new bubbles being formed. But they tell you more than that. Now I'm going to make some big bubbles just by putting a bottle in the water. And the sound is very, very different. So it's not very elegant. I've just got my thumb over the top, and I'm going to put this down below and let bubbles of air come out. And you're all familiar with that sound. But the interesting thing here is that the big bubbles make a deeper note and the smaller bubbles make a higher note. So they're like big and little bells. So when you hear this ping noise of a new bubble being formed, it's telling you how big it is. And it's a very precise relationship.
Bubbles make sound for the same reason many other things do. They vibrate or oscillate. They do this because the air inside the bubble can be squashed, and then the squashed air pushes back. But a few years ago, some colleagues and I wanted to solve a mystery. What starts bubbles oscillating in the first place?
If you think of bubbles like bells, it's a bit like asking, what is the hammer that hits the bell? What gets it started? So in order to answer that question, I took this series of photographs. And what you're looking at here is a tube of air where an air is being blown upwards into water. And this is the moment that the bubble breaks away from the tube and escapes up into the rest of the water column. So you can see right here that just as the bubble starts to break, it generates this neck which narrows. And then as we carry on in time, it gets narrower and narrower. And then this is the last moment that the bubble is attached to the rest of the gas before it breaks away. And in the next frame, 1/10 of a millisecond later, it's over, the bubble is free. And what we found is that the sound all originates from this point. Bubbles hate sharp corners, and that bubble's got a corner. So all of that liquid rushes up inside the bubble to get rid of the corner. We get this little jet that squeezes the air inside the bubble, and that's what starts these oscillations. So we could actually physically see the hammer hitting the bell.
It's astonishing to realise that all of these sounds are the sounds of bubbles being made. But how about animals that live in water? Then the relationship between bubbles and sound is incredibly important.
Imagine you're a sea creature and you're not just living in an ocean, but you're living in a bubbly ocean. Now, most marine creatures get a lot of their information from sound. So they know about what's going on in the world around them because sound is coming to them. And bubbles are directly affecting that sound. They're absorbing it and they're scattering it. So if you're a marine creature, the bubbles are directly affecting your perception of your world.
Humpback whales hunt small fish by exploiting the acoustic properties of bubbles. The whales blow columns of bubbles and also send sound into those bubbles, which is trapped by them. This terrifies the fish and makes them easy prey for the whales. The way bubbles vibrate and interact with sounds can be exploited by humans too.
Now then, I have here
This is Professor Tim Layton, my scientific mentor and probably the world's foremost expert on bubble acoustics, the relationship between bubbles and sound.
Cold water doesn't clean them.
And what he's about to show me is, well, it's almost like magic.
Here we have a device that we've built. It's a black cone. You could fit it on the end of a tap or in a portable on top of a fire extinguisher or something. And just cold water is coming out of it.
This is an experimental rig which, thanks to bubbles, could one day completely change the way we clean things.
Lipstick is notoriously difficult to remove because it's designed to be sticky. And if we take this Northern kitchen towel and we were to say, right, I'm not very good writing with lipstick, say B, B, C on it, like this. And then we hold this into the stream of cold water. As expected, it stays on. It's really good at sticky.
Now, with a flick of the switch, the magic happens.
And here we go.
It's stunning.
And cold
the difference
water-
is amazing.
This incredibly effective way of cleaning relies entirely on bubbles and their relationship with sound.
Water comes through this device, and we add microscopic bubbles, and we had ultrasound using this silver sound source at the back. And when the bubbles hit the device to be cleaned, the ultrasound hits them and turns these bubbles from nice little balls of gas into quite excitable little scrubbing machines.
This works because the bubbles are resonating, vibrating in response to ultrasound, the high-frequency sound waves that are traveling through the water.
The wall is shimmering and moving very rapidly with thousands of tiny little ripples. And at the edge of those ripples, you have very high shear in the water. And so what that does is it scrubs away at any surface.
So shear is like this sort of action.
That's
so
right.
It's scrubbing.
Yeah, so it's scrubbing. So it really is scrubbing away at the surface, cleaning away, removing dirt and particles. So the bubble wall shimmers to clean, but specifically using the bubbles in this way, they're targeted to seek and find crevices and cracks and clean the dirt out of those.
This is the second really clever bit. The vibrating bubbles send out sound. This echoes off nearby surfaces, and the reflected waves pull the bubbles closer to those surfaces and into any tiny cracks that exist. Those crevices are exactly the places that are usually hardest to clean.
So it's really strongly attracted into that crevice, and it burrows into it, keeps burrowing, digging out the dirt as it goes because its surface is shimmering.
And what sort of applications has this got out in the real world?
We're looking at, first of all, manufacturers with production lines, with big plants. Right at the other end of the scale, we would like to see one of these in every home and every hospital so that hands, scalpels, endoscopes, and anything else that you want to clean is safely cleaned. And not only that, but cleaned using cold water with very little additives so that you're not wasting water and so that you don't incur the energy bills and the cleanup bill to make that water drinkable after.
And all that is possible because of tiny bubbles that we can't even see.
Exactly.
So we're going to give you the microbubbles now. 3, 2, 1, inject.
This is Charing Cross Hospital, and here they're using the way that bubbles respond to sound very differently. To see inside a person. They're injecting microscopic bubbles into the patient's bloodstream. These bubbles dramatically improve the quality of ultrasound scans, giving doctors a much better chance of making an accurate diagnosis.
Breathe in, sir. Hold your breath there, very still. Perfect. There you go. Can you see how it's enhancing all around that lesion now? There is a contrast in here, you see? All done. Didn't feel much at all, hopefully. Good. Perfect.
Normally, ultrasound works by sending high-frequency sound into the body and listening to the echoes that come back. The problem is there isn't much contrast between different tissues of the body. But if bubbles are present, the ultrasound makes them vibrate and scatter sound. This makes the echo that comes back much stronger. At Oxford University, my friend and fellow bubble scientist, Dr. Eleanor Stride, explains.
So we put these very, very tiny bubbles into the bloodstream, and suddenly you're able to see where the blood is flowing. If I show you an image of that in action. This is a scan of the liver. This is before the contrast agent has got to the liver. What you'll see when I start the video is the contrast agent starts to wash into the blood vessels.
So the bubbles are coming. Oh, and you can see all these little tendrils that are... And those are the blood vessels?
Those are the blood vessels, exactly. So because the bubbles are in there, they're reflecting the sound really strongly. Yeah, there we go. You see the major blood vessel here and the smaller ones branching off it.
So we can see there's a lot of blood in this area here.
Yeah, and out really nicely and clearly. And you can't see those under normal ultrasound imaging. And this is what bubbles provide.
So you can see abnormal tissue, basically.
Precisely.
Bubbles resonate like musical instruments. That's the secret behind many of the things we're now using them for. But there's another aspect of bubble science, with perhaps the most surprising consequences of all. It's to do with the way bubbles move through the liquid and carry things to the air and back. This affects many aspects of nature, and we'll see how it's vital to our oceans and atmosphere. And to see how that works, I want to show you how bubbles do what they're most famous for: perform their magic in champagne.
I've got quite mixed feelings about today because, on one hand, this is the bubble physicist's dream day out, and it's something I've always wanted to do. And on the other hand, I'm never going to live this down because this is the Champagne region of France, and I'm here to spend the day in a laboratory where they study champagne. But would-be teasers take note, there is a scientific reason for this, because bubbles are crucial to how we taste and perceive champagne.
Before going to the lab, I start my investigation into how bubbles work in Champagne in one of the classiest restaurants in Reims, the capital of the Champagne region.
Starting with a big one.
I'm here with sommelier Philippe Jamès and physicist Gérard Ligier-Belair, who studies champagne bubbles. To show me how important bubble movement is in champagne, they subjected me to a test. They've poured the same champagne into 3 differently shaped glasses. Apparently, the bubbles will move differently in the different glasses. And that, in turn, will change the way the champagne smells and tastes. But I was doubtful I'd notice, because when it comes to champagne, I'm a complete novice. It is actually really different. And that one's much, it's like, it gets a lot calmer. In a tall, thin glass, the bubbles reaching the surface are bigger and are moving faster than in a wide glass. That makes the drink smell and taste very different. To find out why, I went with Gérard to his lab at the University of Reims. A lab dedicated to the study of champagne bubbles.
About 15 years ago, I got interested in bubbles, especially by drinking, not champagne, I was too young, but I was drinking beer, indeed. And I focused on the tiny bubble trains on the beer wall, on the glass wall, and I imagined that it could make a fantastic PhD project. So from the fluid mechanics point of view.
In vino veritas.
You're right, in vino veritas, yes. I knew that obviously bubbles are very important in the champagne industry. So maybe I could mix my passion with bubbles with the champagne industry if they want to know more information about their bubbling process.
Champagne bubbles are full of carbon dioxide, a gas made while the drink was being fermented. When the bottle is sealed, the gas stays dissolved inside the liquid. When the cork comes off, the gas escapes as bubbles. The glass they're in has a big influence on their journey. Gerard wanted to know how that process starts, how the bubble forms.
What's this showing us?
Yeah, this is champagne, and we have fitted microscope objective on a high-speed video camera where the bubbles are coming from.
And so where are they forming?
They form everywhere where a tiny particle or imperfection is. So we are going to see this on the screen. You can clearly see that the bubbles are not coming from nowhere. They are coming from a tiny particle stuck on the wall. And this is indeed a tiny dust particle.
So they're actually coming from specks of dirt?
Yes, it's dirt. Yes, you're right.
Gerard had shown that bubbles are born wherever there are imperfections on the glass's surface. And this has surprising consequences.
This says to me that you can artificially make places. You could choose that your champagne glass would make more bubbles.
When you see such a column on the center of the glass, it is because the glass has been etched
So they've
artificially.
scratched away
Yes.
at the bottom
Yes.
to make these rough surfaces.
Yes, to promote effervescence.
By putting dye into the champagne, you can clearly see the effect of scratching the bottom of the glass. It forces the bubbles to travel in a narrow column up the center of the glass. And we'll see that this is really important.
The lovely thing that I think that's really clear here is that you can see that the bubbles are starting really, really tiny and they're being released and they're growing as they go up, and as they get more and more buoyant, they get bigger, they go faster and faster.
Yes, because the CO2 continues to accumulate inside the rising bubble, so it grows inside and it accelerates.
So in a tall glass, the bubbles travel further and they get bigger and they're moving much faster than they do in a short glass. This has the effect of mixing the drink more vigorously, which in part explains the more intense flavour I'd noticed in the tall, thin glass. But that's only half the story. With his high-speed camera, Gerard found the bubbles do another crucial job in champagne.
So here we have a high-speed photograph of the champagne jet, which is ejected by the bubble, and we also have a high-speed film of the process.
So this is just as the bubble is just at the surface and it sits there for a little while, and then the sort of top of it breaks.
Absolutely.
And this is what happens
Then
next.
the bubble cavity collapses, and when it collapses, it can eject a tiny champagne jet up to several centimeters above the surface.
Gerard now went one step further. He analysed the droplets being spat out by the bubbles. The molecules that carry the distinctive aromas of champagne were really concentrated in the droplets. They'd been carried by the bubble, somehow sticking to the bubble surface.
Bubbles has carried obviously CO2, but also aromatic molecules stuck on the bubble wall. And when the bubble collapses, it ejects all those molecules above the surface.
So this moment here, right where we see the hole in the water, that hole is coated with these molecules.
Right.
And then when it squirts it upwards,
Yes.
those molecules
All the
are
molecules are
ones
growing, yes.
up into the air.
Yes.
That's just I love all this photography. It's fantastic. We've watched this all day.
It's a very efficient way to transfer the champagne into the vapor phase so that you can feel it with your nose.
What Gerard had found in the champagne is a property of bubbles that's really important. As we'll see, it's crucial to our oceans and our atmosphere. Bubbles have the ability to transport substances from within a liquid to its surface and beyond. But why? What's going on their surface, this mysterious place where gas and liquid touch, that means certain molecules stick to it? It's hard to show because these molecules are invisible. So I've come up with another example.
And so what I've got down here is an experiment to show how bubbles can carry glitter. And glitter is like those aroma molecules here because it doesn't want to be underwater. If it can find a place where it's touching both the water and the air, it will stick there.
Parts of these molecules are repelled by water, so they rush to the one place where there's no water, the surface of the bubble.
So the way that this works is I'm just going to take lots and lots of photographs, and hopefully one or two of them at least will show the glitter sticking to the bubbles and being carried up to the surface. So let me set this going. So I'm going to push down on the plunger, which is going to send air down here and out through the funnel where the bubbles are. So now I can look at the photos and see if I can see the bubbles carrying the glitter upwards. Okay, so here's one. This is really, really nice. There's a big whoosh of bubbles have all come out together, a cluster of them. And you can clearly see that the glitter is just stuck to the surface of the bubbles, and there's actually a little cloud of glitter at the bottom where bits have fallen off, and so they're leaving a trail of glitter behind them as well. So it's really obvious here that the bubbles are carrying glitter upwards.
The fact that certain molecules can stick to bubbles is incredibly important and has inspired some very exciting medical research.
What we're doing is we're pumping liquid through one channel, gas through another channel, and where they meet, we're getting a bubble.
Scientists hope that bubbles will become magic bullets. It's all about the bubble surface. The basic idea is that instead of glitter, scientists will stick drugs there.
We're actually attaching a cancer chemotherapy drug right onto the bubble surface.
So if you have a drug that's got the right properties, it will stick
It'll stick to the bubble. Exactly. It'll stick right onto the bubble surface, and it won't come off until we want it to come off.
And how small are these bubbles?
Really, really tiny. Their equivalent size is a red blood cell, so that they can go through the capillaries within the body just that much easier. They won't get filtered out by the lungs. They can go where they need to go, and we can use them for both diagnostic and therapeutic applications.
But there's a second really important benefit to using bubbles to carry drugs. They can target specific places in the body. That means the drugs they carry don't affect the rest of the body, and this helps avoid damaging side effects. One really clever way of doing this is for the bubbles also to carry tiny particles of iron, so they can be directed by magnets.
So this is a bit like that. It's a very sophisticated version of that thing where you get iron filings and a magnet, and as you pull the magnet around, you can pull the iron filings around.
Yes, it is exactly like that, except this time we just see bubbles moving as opposed to iron filings. So you can see at the top, there's a brown layer.
So it's brownish because it's like rust.
Yes, basically.
Rusty bubbles here.
Rusty bubbles,
All
yeah.
right.
But they're not bad for you in any way. And then if you bring a magnet nearby, you can actually see the cloud actually move down. And then when you move it away, it turns.
Are they well behaved? Look at that.
Yeah. So
That's lovely.
Yeah. So these.
So you can really push and pull them around.
Yeah, but wherever the magnetic field is strongest, that's exactly where they'll head for.
Once you put your magnets on the person, how do you know whether the bubbles have stopped in the right place?
So we can actually see the bubbles completely under ultrasound in real time. So that's one of the amazing things of these. With other drug delivery vehicles, you have no idea where they are. You hope for the best. With this, you actually see them stop. You can see exactly where they are. And then you can actually, when you remove the magnetic field, you see them go away.
So have you got pictures of that? That sounds fantastic.
Yes. So on this screen here, we actually have a video I recorded earlier on. So this is the tube, the outer wall, and you can see the inside completely empty because there's no bubbles.
So this is like a blood vessel, a capillary vessel,
Yes.
somewhere in the body, and the cells over here, and blood is running.
Exactly, yeah. And below here we have our magnet. So it's sitting a bit of a distance away, I think it's about a few millimeters. So when I press play, we'll actually see bubbles then flow in.
So things are flowing through the pipe, but we can't see anything.
Yeah.
And here are the bubbles.
Yeah. So you can actually see they're being drawn down towards the magnet, and then on the bottom you see an increase in bubble
So
concentration.
here's the magnet, and here are all the bubbles that are attracted to it.
Yeah.
And that would be where your tumour was, or wherever it was that you wanted to treat.
Exactly, yeah.
If this research works out, one day bubbles will carry drugs to exactly where they're needed. Once there, the final step is to persuade them to release their payload of medicine. And to do that, we exploit the way bubbles respond to sound.
When we want to use them for drug delivery, though, we just turn the ultrasound energy up, they oscillate more violently, and the drug is released.
So that's lovely, because you sort of, you keep them calm, little
Exactly.
ultrasound, and then when it's time, you thump them with sound. Oh, that was a big clap. And,
Well, that's actually exactly what happens. The bubbles expand to a large extent, and then they collapse. And it's the collapse that releases the drug and destroys the bubble.
So you got a video of this collapse process?
I do indeed. So these are images taken at a few million frames per second. Sound comes in, see the bubble expand, contract, and then break open and release its contents.
That's great. So just like you might be injected in the arm with a vaccine or something, this is injecting the drug into the body.
Fact, bubbles have been described as microsyringes because one of the interesting things about this jet is being emitted very, very fast, and it's sufficiently fast to actually puncture a cell membrane.
So the cell doesn't have a choice about this.
The cell doesn't really have a choice, no, provided the jet's in the right direction. The bubbles provide a fantastic way of encapsulating a drug, so the drug will have no action on the body until it's released. The bubbles keep it encapsulated. It's packaged, exactly. And more importantly, it's packaged in something that we can track, because we can track where the bubbles are flowing under ultrasound.
Someone was going to say that to me in live.
It's great to see the direct practical benefits of bubbles. But now it's time to bring together all the things they can do and see how the tiny bubble matters to our whole planet. Most of the Earth's bubbles are here, in the oceans. They're formed as breaking waves drag air underwater. These are the bubbles I study. And the reason I study them is that bubbles influence the way the oceans and atmosphere interact. And they do so in ways we're only just beginning to understand. I observe bubbles at sea, and I also study them in great detail in my lab. Here, I can replicate the great variety of conditions that exist in our oceans.
So what I can do with this tank is basically make it into any region of the ocean that I want. So it might be somewhere in the tropics with a high water temperature and lots of phytoplankton. It might be somewhere in the Southern Ocean, the water's very, very cold, not so much growing, and I can watch how the bubbles form in all those different situations in the ocean. And what's happening is that down at the bottom there is a nozzle, and it's bubbling away, so it's producing lots of bubbles. And those bubbles rise into a region where there's two tubes coming down on either side, and they're pumping water out. And so those bubbles rise up in a straight line, and then they hit this region of turbulence, and that's just like what happens to bubbles underneath the breaking wave.
The reason for trying to understand bubbles is that out in the ocean they play an important role in our climate. One part of that role especially is brilliant because it's so surprising.
When they rise to the top and they form that foam, the white horses on the ocean surface, they are spitting tiny particles up into the atmosphere. And those particles can be bits of salt, or they can be sort of organic material that was stuck to the bubble. And they all get spat up into the atmosphere. And that matters. And I love, this is one of my favourite facts in sort of bubble science. Those tiny particles that get spat upwards help clouds form. So in a cloud in the atmosphere, all the droplets have at their centre a little speck of dust of some sort. And especially over the open ocean, the clouds quite often at their centre have a little speck of dust that was spat out of the ocean by a bubble.
And ocean bubbles aren't just a one-way street. They also help carry gases like carbon dioxide and oxygen down into the water.
And so these transport mechanisms, the fact that the bubbles help gases move around and help particles move around, is really important for weather and climate because it's basically changing the chemistry of both the atmosphere and the ocean.
So you can see why knowing how many bubbles there are and how big they are would help our climate models. And this is the equipment I'm using to do this. It records bubbles responding to sound. In principle, by analysing these recordings, I can calculate how many bubbles there are in a particular part of the ocean. And equally important, I can estimate how big they are. The idea behind how this works is quite simple. And so you can see now very clearly that there's this long period oscillation that's the bigger bubble. And this has a frequency of 1.7 kilohertz, tells me that the bigger bubble here was about 2 millimeters in radius. And the frequency of the other one is 16.5 kilohertz. And that tells me that this bubble here was about a tenth of the radius. So this one is about 0.2 millimeters in radius. And you get all of that information just from looking at that sound signal. And this is why sound is such a powerful technique to use in the ocean, because all you have to do is listen and you get this huge amount of information about what just happened. It's early days. There's much more work to do to compare the laboratory results with our measurements at sea. But one day, I hope to be able to estimate not just how many bubbles form and how big they are, but exactly when and how they matter most. And then that information can be added to our climate models. By understanding bubbles, we'll have a better understanding of our planet. At the beginning of this film, I quoted Lord Kelvin talking about the physics that we can learn from bubbles. I hope that I've persuaded you that what you might have thought of as beautiful toys are enormously powerful scientific tools. They can help us explore nature at scales that are normally beyond our reach. They have surprising practical benefits too, in diverse fields such as ship design and medicine. I hope that from now on, you'll see bubbles in a completely different way.
Imagine just one bubble and all the things it does while it exists. And then remember that underneath every breaking wave, there are millions of bubbles. And under every storm out at sea, there are millions of breaking waves. And on our planet right now, there are tens or hundreds of storms going on. So overall, on Earth right now, there are billions of bubbles out there. And the key to understanding all of what those bubbles are doing is understanding just one object, one little bubble. And the thing about bubbles is that once you know a little bit about them, you start seeing them everywhere and start appreciating what they're doing. And so understanding just one physical principle means that you start spotting it everywhere in your everyday world. So just one bit of physics can make your life so much richer.